Hello everyone. We are starting a detailed technical series on energy efficiency improvements in 3GPP technologies, especially LTE, 5G and 5G advanced. Energy efficiency has become one of the most important topics in mobile networks. It affects network cost, sustainability, equipment design, radio planning, operations, automation, and future standardization. But before we jump into specific LTE and 5G features, we need to understand the basics. What exactly do we mean by energy efficiency? How is it different from energy saving? Why does the radio access network get so much attention? And how do operators actually measure whether the network is becoming more efficient? This first video is about those foundations. In the next videos, we will go deeper into LTE energy saving, 5G NR design choices, 5G advanced release 18 network energy saving, and then release 19 and future energy aware networks. Let us start with why energy efficiency matters. Mobile networks are expected to do more every year. They need to support more traffic, higher capacity, better coverage, more services, more devices, and more demanding use cases. Video traffic continues to grow. Cloud services, IoT, enterprise applications, private networks, fixed wireless access, XR, and AI related traffic all add to the demand. At the same time, operators are under pressure from energy cost. Electricity is a major part of network operating expenditure, so reducing unnecessary energy use is not just about sustainability, it has a direct financial impact. There is also the carbon and sustainability angle. Many operators have committed to net zero or carbon reduction targets, and network energy consumption is a big part of that journey. And finally, the networks themselves are getting more complex. We now have more frequency bands, denser deployments, massive MIMO, carrier aggregation, small cells, private networks, cloud RAN, open RAN, edge computing, and network slicing. So energy efficiency is not simply a green initiative. It is a technical, financial, and strategic requirement. The challenge is to deliver more capacity and better services while managing cost, carbon impact, and operational complexity. When we talk about mobile network energy consumption, the radio access network or RAN gets most of the attention. The reason is simple. The RAN is usually the most energy intensive part of the mobile network. A mobile site includes active and passive antennas, radio units, baseband equipment, power supply, backhaul, and cooling. In some cases, backhaul may be fiber, while in other cases, it may include a microwave dish. All these elements contribute to site power consumption. The radio unit is especially important because it contains the RF components that transmit and receive signals over the air. The power amplifier is a major part of the radio energy story because it has to generate enough output power to support coverage, capacity, and quality of service. This is why many energy saving techniques focus on RAN. If we can reduce unnecessary radio transmissions, turn off unused carriers, adapt antennas, reduce transmit power, mute resources, or put parts of the base station into sleep states, the impact can be significant. But we must also be careful. The RAN is not just a power consuming system. It is the part of the network that provides user coverage and radio access. So any energy saving has to be balanced against availability, accessibility, throughput, latency, and mobility. A common mistake is to use energy saving and energy efficiency as if they mean exactly the same thing. They are related, but they are not the same. Energy saving means using less energy. For example, if a cell has no traffic at night and we switch it off, we reduce energy consumption. If a device sleeps for longer, it saves battery. If a site uses less power over a period of time, energy has been saved. Energy efficiency is about useful output per unit of energy. For example, how many bits are delivered per joule? How much coverage is provided per kilowatt hour? How much traffic, service quality, or user experience is delivered for the energy consumed? This distinction is important for mobile networks. A 5G site may consume more absolute power than an older 4G site because it has wider bandwidth, more transceiver chains, and massive MIMO. But if it delivers many times more data, better capacity, and better spectral efficiency, then its energy efficiency can still be better. So, energy saving is about using less, while energy efficiency is about getting more from what we use. Both are important. A good network strategy needs to reduce waste while improving the useful output delivered by every unit of energy. To improve energy efficiency, we first need to measure the right things. Let us separate three related concepts. First, energy consumption. This is the total amount of energy used over a period of time. It is typically measured in watt hours or kilowatt hours. Second, power consumption. This is the rate at which energy is being used at a given moment. It is measured in watts or kilowatts. Third, energy efficiency. This tells us how much useful output or service is delivered for each unit of energy consumed. In telecoms, a common way of expressing energy efficiency is bits per joule. Another practical network metric is data volume per energy consumed. For example, gigabytes per kilowatt hour. For RAN coverage, we may also think about coverage area per energy consumed. For service level analysis, we may consider user sessions calls, QS output, or other service metrics per unit of energy. The key point is that the right metric depends on what we are measuring. Are we measuring a piece of equipment, a radio unit, a cell, a base station site, a G node B, a network area, a slice, or a particular service? One metric cannot answer every question. This is why measurement context is so important. Now, let us look at one of the most important ideas in network energy saving. Traffic varies a lot by time of the day of the week, and location. A business district, a residential area, a stadium, a shopping center, and a rural site will all have very different load patterns. Networks are dimensioned for busy periods. Operators need enough capacity when demand is high. But for much of the day, many cells are at low or medium load. The problem is that base station power consumption does not fall in the same way as traffic. In an ideal world, if the traffic dropped to 10%, the power consumption would also drop close to 10%. But that is not how real base stations behave. Even when there is little traffic, the network still needs to support coverage, signaling, synchronization, paging, mobility, and basic availability. Some hardware remains active. Some common signals continue to be transmitted. Some resources remain ready for users arriving in the cell. This creates a gap between traffic load and power consumption. That gap is the energy saving opportunity. This is why so many LTE and 5G energy saving techniques focus on low and medium load periods. Can we switch off a capacity layer? Can we deactivate a secondary carrier? Can we mute transmissions? Can we put part of the radio into sleep mode? Can we adapt antennas or transmission power? Can we wake the resources quickly when needed? The biggest gains often come from intelligently managing these low and medium load periods without harming the user experience. To manage energy efficiency, operators and vendors need measurement methods. The first type is static measurement. Static measurements are common in labs and procurement. The idea is to test equipment under controlled conditions at fixed load points. For example, the equipment might be tested at low, measurement, and high load. At each point, we measure power consumption, throughput, and energy efficiency. This is useful because it is simple, repeatable, and comparable. It allows operators to compare equipment, evaluate vendor claims, and establish benchmarks. Static testing gives a clear view of power consumption at key operating points, but it has limitations. A real mobile network is not static. Users move, traffic is bursty, radio conditions change, interference changes, weather events and mobility all affect behavior. Network features also interact with one another. So static measurements are only part of the story. They are useful for controlled evaluation, but they do not fully capture real-world dynamics. This is where dynamic measurements become important. Dynamic measurements try to capture how the network behaves over time under changing conditions. Instead of looking only at fixed load points, we measure power consumption, traffic load, throughput, and other KPIs as the load changes throughout the day. In a lab, dynamic testing may use UE emulators and traffic models to create more realistic behavior. In the live network, dynamic measurement can use operational data, counters, power meters, sensors, and OAM systems. The advantage is that dynamic measurements show patterns. They show what happens at night, in the morning, during the busy period, in the evening, and during low load again. They help identify where energy is being wasted, where sleep modes are effective, where traffic and power are mismatched, and where improvements can be made. Dynamic measurements are especially useful for validating energy saving features. It is not enough to say that a feature reduces power. We also need to see what happens to throughput, latency, accessibility, handover performance, and user experience. So static measurements give controlled snapshots. Dynamic measurements show the behavior over time. Both are needed. Measurements become useful when they are turned into KPIs. A KPI or key performance indicator is a metric that helps us understand how well the network is performing. For energy efficiency, KPIs should not be looked at in isolation. We need energy KPIs, but we also need performance and quality KPIs. For example, availability and reliability KPIs tell us whether the network remains accessible. Throughput, latency, call setup success rate, and packet loss tell us about service quality. Traffic and utilization KPIs tell us how network resources are being used. Then we have energy efficiency KPIs such as energy consumption, bits per joule, or kilowatts hours per gigabyte. Cost efficiency KPIs may also be important such as power cost per site or energy cost per gigabyte. This is important because saving energy by damaging the network is not a good result. If a cell is switched off and users lose coverage, the energy bill may go down, but the network experience suffers. So the right approach is to look at energy KPIs together with service KPIs. That helps operators identify where energy can be saved while maintaining coverage, quality, and customer experience. The aim is not just to collect data, the aim is to measure what matters. Measurements only become valuable when they lead to action. A practical improvement process has 5 stages. First, measure. Collect accurate static and dynamic measurements across the network. Second, analyze. Look at KPIs to understand performance, identify issues, and uncover root causes. Third, decide. Prioritize the problems, define the right solutions, and plan the actions. Fourth, optimize. Implement the improvements. This might include parameter tuning, feature activation, load balancing, site upgrades, carrier management, antenna adaptation, sleep mode configuration, or automation rules. Fifth, verify. Measure again to confirm whether the change delivered the expected benefit. This creates a continuous improvement cycle. In energy efficiency, this cycle is essential because networks change all the time. Traffic patterns change, new devices appear, new services are introduced, software is upgraded, new spectrum is added, seasonal and event-based behavior can also change the load profile. So energy optimization is not a one-time activity. It is a continuous loop of measurement, analysis, decision, optimization, and verification. Good measurements require good discipline. First, define clear objectives. Know what you want to measure and why. Are you measuring equipment efficiency, site energy consumption, cell level energy efficiency, service quality, or the impact of a new energy saving feature? Second, choose the right metrics. The KPIs must align with the network objective. For example, an energy saving trial should include energy consumption, but also throughput, latency, availability, accessibility, and user experience indicators. Third, plan the measurement activities. Decide the scope, timing, frequency, locations, and required resources. Fourth, ensure data quality. Use calibrated tools where required. Follow standard procedures and validate the data. Bad data can lead to wrong conclusions. Fifth, analyze and interpret the data properly. Do not just look at individual numbers. Look for trends, outliers, correlations, root causes, and patterns over time. Finally, take action and follow up. Implement improvements, verify the results, and keep monitoring. The tools can include measurement platforms, data collection systems, analytics dashboards, GIS and mapping tools, and increasingly automation and AI. But tools are only useful when the measurement process is well designed. The goal is to turn data into insight and insight into better network performance. Let us summarize the key points from this first video. First, measurements provide visibility. We need controlled measurements such as static test and real-world measurements such as dynamic and live network data. Second, KPIs turn data into insight. The right KPIs help us track what matters and guide better decisions. Third, measurements drive continuous improvement. Energy efficiency is not a one-off project. It is a cycle of measuring, analyzing, deciding, optimizing, and verifying. Fourth, good measurement practices matter. Clear objectives, the right metrics, good data quality, proper analysis, and the right tools all lead to more reliable results. And finally, better measurements lead to better networks. The aim is not simply to reduce the energy bill. The aim is to build networks that are efficient, high performing, and user centric. The most important message is this: you cannot improve what you do not measure, but you also need to measure the right things. In the next video, we will move from the basics into LTE energy saving. We will look at dormant mode, carrier switch off, cell DTX, compensation cells, OAM based control and signaling based approaches. That is where we will start seeing how 3GPP began turning these energy efficiency concepts into practical network mechanisms. Thank you for watching, and I hope to see you again in the next part.